Hey, welcome back to another video. Today we're talking about the law of conservation, talking about how do we represent physical and chemical changes a little bit further. So starting off here with a little bit of vocabulary, the law of conservation states that matter and energy cannot be created or destroyed. No matter how hard you try, you can't create new energy, you can't create new matter, and you can never destroy it. It can only change its form and its location across the cosmos, across our universe, different parts of our planet. It can go anywhere. Then we got to talk a little bit more about chemical symbols. We've seen a bunch of these already, but a chemical symbol is a letter or pair of letters that represents an element. So for example, hydrogen is represented by the letter H, and aluminum is represented by the letters A and L together. All right. We can then take those chemical symbols and build a chemical formula out of it. So this is a series of chemical symbols, elements, that tells us which elements a compound is made out of. So for example here, this water molecule has the chemical formula H2O. You've probably heard it a lot. H2O is made out of 2 hydrogen atoms, hence the 2 here, and 1 oxygen atom. There's no 1 written here, just don't worry about that. We'll talk about that in a second. Then if we put a bunch of chemical formulas together, we can build a chemical equation, which is a series of chemical formulas that represent a complete, balanced chemical reaction. So chemical equations are the ultimate pinnacle of representing chemical changes. For example here, hydrogen gas and oxygen gas together, when they combine, forms water. So if you did that in the barking dog experiment with the precipitating copper, this is the chemical change that was occurring when that test tube had that explosion happen in it that made that loud noise. But because matter and energy can't be created or destroyed, we have some really interesting things to talk about here. For example, the water you drink today may have been drinking by dinosaurs 65 million years ago. This water you probably have already re-drinking yourself because when you pee, your waste goes to the wastewater treatment plant and they recycle it, they clean it out, and then they return it to our drinking supply. So the water molecules that you have drinking and peed out before, you've probably drinking more than once. A little gross to think about, but they're just water molecules, right? All of the pee stuff has been filtered out chemically. A bit sadder here, since matter and energy can't be created or destroyed, everything that we make, everything that we throw away, everything that we don't recycle is out there somewhere in the world. And last year, in 2023, we threw away 4.5 trillion pounds of trash. In 2050, there will likely be more plastic in the ocean by weight than fish. If you imagine your house is more trash than people, that's disgusting. And we need to find some way to change this. Okay, but it gets a little bit more interesting and a little less dark here. So about 50% of our water molecules are replaced every 8 days. All of the water in your body is usually recycled within a month or so, or 16-ish days. 50% of the carbon atoms in your body, so this is the main reason why we eat food, is to get carbon for sugars, for energy, and we breathe it out as carbon dioxide. About every 2 to 4 months, all of the carbon atoms, well, half of them at least, are replaced in your body. And about 50% of the iron atoms, which iron is in your blood, that's what carries oxygen to your body, it's replaced every 6 to 12 months. So over the course of 5 to 7 years, pretty much every atom in your body is replaced with new atoms, which means that some of your atoms were once part of someone else. And if all of your atoms are changing every 5 to 7 years, have you always been the same you? But another interesting realization is that all of the atoms in your body were once a part of the stars. And one day, the atoms in your body will be part of the stars again. Or a black hole, but a little bit more positive. Think about a star. So, all right, this is really cheesy, but even on the days when you don't feel like it, you are made out of star. All right, you are a star. You can do it. You've got this. Okay, don't forget where you came from. Okay, but we'll talk a little bit more about the chemical symbols here. So we have 118 chemical symbols to represent our 118 elements across the periodic table. Most symbols are the first 2 letters of an element name, with some exceptions. I'm not going to go through them. You don't have to memorize them. But if you're interested, all right, the Latin ones I have up here. And we also have some single letter symbols for some of our elements that were discovered really long ago. But if you notice, we only have 26 letters in our alphabet and 118 elements, so we were going to run out of letters eventually and have to go to 2-letter symbols. Okay, but then going back to that chemical formula, all right, these are ways to represent compounds and molecules, which are combinations of elements. Some have some common names that we know. For example, you've probably eaten salt. You do it daily. It's part of your diet. The chemical name for it is sodium chloride, but the chemical formula is a mixture of sodium and chlorine. This is an L here. Some people will get this confused for an I, but this is Cl, not Ci. Okay, if you've had vinegar before, though, that's acetic acid is its chemical name, and its chemical formula is HC2H3O2. Kind of neat. This H doesn't join the other H's because it's special. We'll talk about that later on in the year. It's what makes it an acid. Bleach here is just sodium hypochlorite, so NaClO. Gasoline, its main component is octane, which is C8H18 would be its chemical formula. Baking soda, if we've done any baking before, is just sodium bicarbonate. Its formula is Na, so sodium, H, hydrogen, C, which is from carbon, and O, which is from oxygen, but there are 3 of them. And then the chalk that we worked with the other week, or if you've done sidewalk chalk before, is calcium carbonate, which comes from Ca for calcium, C for carbon, and O3 for those 3 oxygens, right? So those little numbers that I read out are called subscripts. Sub, you can think submarine, they go underneath, all right? So in this case, the subscript H2O tells us that there are 2 hydrogens in a water molecule. And then there's a hidden one here. So we usually don't write it because it's just a waste of time. We could just leave it blank and have people assume, well, if you wrote the O here, there must be at least 1 oxygen. But there is a hidden secret O there. We won't write it, and it'll be wrong if you do write it, but it's still there. It's secret 1. Okay? So that number in a chemical formula that tells us how many of the atoms there are is just that subscript again. And if we have no subscript, we assume it's just 1. Okay? All right. Now, chemical equations is the full combination of all of these aspects. So they're like recipes for chemical changes. So imagine that you take a chicken patty, you add on some buns, you add maybe some lettuce, maybe you're feeling like some lettuce, and then you got some kind of sauce. I don't remember what sauce this is, but it looks kind of gross actually. But if we put them all together, we get a chicken sandwich, which sounds absolutely delicious right now. Okay? And you can think of this as ingredients put together to make a product. Now, for our chemical equations, we can think of this very similarly. All right, so our chemical equation is like a recipe for a chemical change. All right, our reactants are like the ingredients, which we'll put on the left, and our products are like the finished product, the food that we made, which we show on the right side of a chemical equation. Okay, so here would be a chemical equation. In this case, this is what happens when you have natural gas come into your home, if you've got a gas burner for your stove or you burn gas for your fireplace. So CH4 is methane, so it's a carbon. It's a carbon and 1, 2, 3, 4 hydrogens combined together. All right, and we add on, whoa, wait, here's this number 2. This is a coefficient, and the coefficient tells us how many reactants or products are involved in this chemical equation. Okay, so we have 2 oxygen molecules that we add on here, and it's a gas. And when we burn this, we produce carbon dioxide, just 1, so 1 CO2 molecule, 2 oxygens, 1 carbon. And we provide also 2 water molecules. So we got 1 here, and we've got 1 here as well. Each one has 2 hydrogens and 1 oxygen based on those subscripts. Okay? So again, those reactants are CH4, which is methane, and O2, which is oxygen. And our products are carbon dioxide and water. And those coefficients, right, the 2 here and the 2 here, tell us that there's 2 oxygen molecules that are reactants and 2 water molecules that are products. If a coefficient isn't written, you can also just assume it's 1, similar to subscripts. Okay? So if we wanted to represent this with a particle drawing, all right, and remember, I have to have the same number of atoms on the left as I do on the right if I want to show the conservation of matter. Those atoms can't be created and they can't be destroyed, okay? So the way I'd represent this, all right, here's our chemical equation again. And let's not forget these are gases, so as they bounce around, eventually they'll collide together. And when they collide, what happens over here is a chemical change occurs that swaps the positions of the atoms, and so we get 2 new different chemicals. We didn't have carbon dioxide and water before, but we do now. And all 3 of these molecules, the 2 water molecules and the 1 carbon dioxide molecule, are all gases, so they'll still be bouncing around as well. All right. Now, if you count them up, we have 1, 2, 3, 4 oxygens on the left, and we have 1, 2, 3, 4 oxygens on the right. We didn't make any additions or subtractions in our number of atoms. They're still all there because they cannot be destroyed ever. There's nothing you can do to destroy them. Okay? Now, you could talk about nuclear chemistry. We could tear them apart in other ways, but these atoms, for our intents and purposes, will stay the same as they switch their positions and rearrange into new chemicals, new molecules. Okay? There is also a release of heat energy when this happens, so you could think of heat as another product of this reaction. A topic for when we get to thermodynamics. But again, since matter can't be created or destroyed, we have the same number of atoms on both sides of our product, right? Our particle diagram, before and after a chemical change. That's all. I tried to make this one a little shorter. Didn't really work out. Sorry about that. But checkpoint quiz is ready for you. Here I've got some rhodopsite, I think is what it's called. I'd have to double check that. Really cool crystal. And another song recommendation for y'all. This one is a country song. I'm not really a country guy, but I'll forgive this one because he talks about a physical change turning coal into diamonds. So I can forgive it. Anyway, take care. See you, chemists.